We're ready to start our last topic of this course. Ready and excited to start our last topic of this course. I should say that this is what we're going to do is really just an introduction to a broader topic. We're just going to touch some aspects and really get the ideas, but without going into too many details and too many examples and too many theorems. It's really more of a survey of ideas that lead us toward where linear algebra continues. So here's an introduction to this introduction. So far, the major mathematical structure which we considered in this course were vector spaces. Right? Vector spaces were the main object of our studies. And a vector space is something that has elements. The elements are vectors. Vectors are sometimes matrices, sometimes polynomials, sometimes n-tuples, but they're vectors. And there are two operations, scalar multiplication and addition. That was a vector space, and there are, of course, some axioms which have to be satisfied. But we know from real life that even simple vector spaces, like let's say R2 or R3, have richer structure than just their vector space structure. For example, so maybe we'll write some stuff. We know that even simple vector spaces like R2 or R3 have a richer structure than just addition and scalar multiplication, right? And what do I mean by richer structure? So I'll do everything in R2 for simplicity. It's easier to draw and easier to picture. So if we think, remember that we can identify points in R2. In R2 is just the two-dimensional plane. We can identify a point, AB, with a vector with an arrow originating in the origin and terminating at the point AB, right? We took that point of view and we discussed complex numbers, okay? So if we think of vectors in R2 as arrows, then we can discuss, for example, so we have angles. What's an angle? If you have two vectors and you think of them as arrows, so here's maybe one vector and here's another vector and everything is living in two-dimensional space. So this is V1 and this is V2. There's an angle between them, right? This is a geometric concept. What's the angle between two vectors, right? And we can measure it. This is something that's there, right? But it's not encoded in the vector space structure of R2. It doesn't show up from the addition and the scalar multiplication. Do you agree? There's another notion. There's the notion of a length of a vector. If we take the vector V1, which we identify with the point where it terminates, we can measure its length, right? So there's a notion of, so we have angles. We can measure length. Right? We can even discuss, and again, this is a geometric concept, right? This is something that has geometry in it. We can even measure the distance between two vectors, right? What's the distance between V1 and V2? What is the distance between these 2 points? And we know how to do this because we did it when we discussed addition of complex numbers, for example. So we can take the arrow connecting them, this arrow and measure its length. The length of this arrow is the distance between v1 and v2. And we know what this arrow is, right? If we call this arrow u, what is u? U is precisely, if you look here, v1 plus u equals v2. So u is v2 minus v1. Do you agree? So let's move this and write it here. And u is just v2 minus v1. And the length of u is precisely the distance between the two vectors, right? So we can measure length and even distance. And even distance. Let's call it d for distance. The distance between v1 and v2 is dv1 v2 is the length of v2 minus v1. Do you agree? The length of v2, the distance between these 2 points, is the length of the vector connecting them. Do you agree? Okay. So angles, length, distance, these are all geometric concepts that exist in the structure of R2. And likewise, they can easily be generalized to R3. And they're there. And if you do courses in physics, for example, you use this stuff all the time. And when you do multivariable calculus, you're going to use this stuff all the time. And these concepts, these geometric concepts, the geometric structure of these spaces is not encoded at all in the linear space structure. Okay? It's not there. It's additional structure. Okay? And that's what we want to now discuss, what we now want to build formally and abstractly such that this structure will appear not only in R2 and R3, but for a general vector space. Okay? And the key ingredient is going to be this mysterious thing called an inner product, which we're going to define soon. So let me add that. These concepts of angles, length, and distance turn R2 or R3 into not just a vector space, but what we call an Euclidean space, named after Euclid. That's what Euclidean space means. Okay, it means these spaces with their full rich structure into Euclidean spaces. Okay, and what we want to define these notions abstractly. For any vector space. Okay? And you may ask, well, why? Why does it make sense to discuss an angle between two matrices, right? If that's where we're heading, why does it make sense to define an angle between two matrices? Or why does it make sense to define the length of a polynomial, right? That's what we're going to do. If we're going to define these notions for a general vector space, a vector space can be a vector space of polynomials. And we'll have the length of a polynomial. Why would that make sense? Why is it worthwhile doing, right? So many times in mathematics, there's a lot of ability to do abstract stuff. Okay, once you have anything, you can generalize it abstractly, but if it's going to be useful, if people are going to be interested in it, it better have applications. It better indeed be useful other than just for the fun of it. Okay? And it turns out that these notions that we're going to define of angles, length, and distances, and the formal structures that we're going to construct, metric spaces and normed spaces, we're going to see this stuff gradually, is in fact very, very useful and gives rise to many, 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 many examples and theorems and theory and applications, which we're not going to be able to touch too much in the scope of this course. That's why I said this is really just an introduction. Okay, we'll see a bit of each, but that's all. Okay, so the key concept, the key ingredient is the inner product. Which is the first thing that I'm going to define. Okay? So is the introduction to this introduction clear? Is it clear where we're heading and what we want to do?
Euclidean is a definition?
Yeah. What we call Euclidean space, is R2 or R3, and in fact Rn, with the additional structure of angles, length, and distances, but we haven't defined it formally yet. Okay, we just said what it is because we know what it is for R2 and R3 from prior knowledge or from just understanding what I just explained. Okay, but we didn't define formally what is an angle, what is the length of a vector. Okay, in R4, for example, we can't touch it anymore in R4, right? We can't draw R4. Okay, so there's still definitions needed here, and that's where we're building to. Okay. Okay, so here's our first definition. Now we're into the details, and now we're back to formality. It's no longer just an intuitive introduction. So let V be a vector space, a linear space, and everything we're going to do from now on, all our vector spaces, just like they were throughout the course, in fact, we didn't discuss, although we had F in general for our field, usually that F was R or C, right? So now it's going to be only R or C. Okay? So let V be a vector space over either the real numbers or the complex numbers. Okay? These are the only vector spaces that we're going to consider. An inner product, that's what I'm defining. An inner product on V is another operation, defined on pairs of elements, just like addition. Addition we define for two vectors, right? Pairs of vectors, we can call them vectors, we know what they are. But while addition, for example, when we add two vectors, we get a vector, right? The sum of two vectors is a vector. The inner product of two vectors is going to be a scalar. Okay? The inner product of two vectors is going to be a scalar, a number. Okay? So it's an operation defined on pairs of vectors, which gives a number. This operation is often called scalar product. Okay? Scalar product, especially in the Euclidean context, in Rn. Okay? Which gives a scalar. It is denoted by these triangular brackets U comma V, That's how we denote the inner product of u and v. This is not the only notation out there. This is the one I'm going to use. Okay, you'll see various notations, for example, in physics or in other places. Sometimes you'll see a vertical bar instead of this comma here between them. Okay, and sometimes these notations have slightly different meanings. So don't be afraid of notation, but this is the notation I'm going to use. Okay, if you see different notation in various sources, like a book or a different course, you have to make sure that you understand if it's precisely this or it's something slightly different. Okay, it is denoted by UV and satisfies three axioms. So just saying there's an operation usually doesn't say too much, but we're assuming that the operation satisfies some properties, just like for addition or scalar multiplication in the definition of a vector space, there are properties that they need to satisfy in order to be called addition or scalar multiplication. Okay? So what are the properties? What are the axioms? So there are three. So here's axiom number 1. The inner product of u and v is equal to the inner product of v and u, but not exactly, rather with a complex conjugate. Okay? So remember that the result of the inner product is a scalar. Okay? The result is a scalar. U comma v is a number. Okay? If we're working over C, then this number and this number are complex conjugates. Okay? So if this gave us a plus bi, this would give us a minus bi. If we're working over R, then they're actually equal. Okay, so maybe we'll emphasize here, over R, UV equals VU, right? Because real numbers, the complex conjugate is themselves, right? So over R, this becomes just equality. That's the first property. It's called conjugate symmetry. This is called symmetry, obviously. This is called symmetry. And in general, it's called conjugate symmetry. Okay? Not symmetry, but conjugate symmetry. Okay? I'll write that. So number 1 is called conjugate symmetry. Good? So that's the first property. Property number 2 is linearity of this operation in the first factor. Meaning, if you take alpha u times v, remember that this is called a product, so I can call it times, alpha u times v, this is the same as alpha uv. Okay, so this is linearity. You can pull the scalar out, right? And if you take addition, u plus w comma v, that equals u comma v plus w comma v. Okay, so this is linearity in the first factor. Do you agree? Okay, so let's maybe write that. Linearity in the first. First meaning the left component. Okay?
Only in the first component?
Well, we'll see. That's the axiom. It has to satisfy this. We'll see what... So you're asking, a natural question would be, well, is it linear in the second component? And the answer will be not an axiom, it will follow from the axiom, so we don't have to impose it as an axiom. Okay? And 3, and by the way, the answer is going to be not exactly. A bit surprising, but not exactly. And property number 3 is that v comma v, if you take the inner product of a vector with itself, you always get something non-negative. Do you remember what it means to say that something is non-negative when we're discussing complex numbers?
It's above the x.
Nope. No. When we have, remember, a priori we're working over C. This may be a complex number. When we're saying that this complex number is non-negative, we're implicitly saying it's real. Okay, there's no order relation on the complex numbers. We mentioned that. Okay, so by this statement is implicitly saying that this number is in particular a real number. Okay, and a non-negative real number. Okay, and furthermore, it could be equal to 0. It could be 0, right, because we're saying it's non-negative. It could be 0, but that's if and only if v is 0. Okay, so the only situation where the product is 0 is when we're taking 0 times 0. Okay? Okay, this property number 3 is called positive definiteness. These are just names, and we're probably not going to use them too much. But nevertheless, I'm mentioning them. Okay, so these are the 3 properties of being an inner product. Okay? Now, it may look very mysterious, very abstract, and probably not too related to what we just discussed about Euclidean space. So we have to carefully work out stuff and see why it is. Okay? What's the relation? And what other properties follow from this? And see some examples. Okay, so there's stuff to come. So let's start with a few remarks. Before we do examples, the most important thing is examples, because when we see examples, things become clearer. We understand what we're facing. But before that, I want to make some quick remarks, a few quick remarks. So let's write them here, remarks. V comma V, so this is remark number, let's call it 1. V comma V equals, by property number 1, VU equals the conjugate of UV, right? So VV equals the conjugate of VV by 1. Do you agree? Okay. But when is a number its own conjugate, its own complex conjugate?
It's real.
When it's real. So from here it follows, so VV is always a real number, even if we're working over C. Okay? And that makes the statement in part 3 that it's a non-negative real number makes it reasonable, makes it make sense. Okay, good? Okay, so this is for every V. So is this remark clear? Okay. Remark number 2 addresses the issue of what happens in the second component. Is it linear in the second component? So the answer is not quite, almost. So let's look at the product of U and alpha V. So I inserted a scalar in the second component now, and I want to see if I can pull that scalar out. Okay? So what I know by the axioms is how to pull out a scalar from the first component, right? And what I also know is how to reverse the order of the components. That's axiom number 1. So by axiom number 1, I can force this scalar to move to the first component. I get alpha v u, but with this complex conjugate, right? This is axiom 1. Do you agree? And now I know how to pull a scalar out from the first component. It just pulls out. That's axiom number 2. So by axiom number 2, this equals alpha VU conjugate, right? Now, the product of two complex conjugates, or sorry, the conjugate of a product is the product of the conjugates. So this equals alpha bar VU bar, right? And then this in turn, using property 2 again, property 1 again, sorry, this equals alpha bar UV. Do you agree? Okay, so it's really playing with the definitions. We get, if you look at both ends, that alpha, in fact, can be pulled out of the inner product, but when it's pulled out from the second factor, it comes out with a complex conjugate. Clear? So it's not linear in the second component, it's conjugate linear in the second component. Clear? What about addition? What about addition in the second component? It turns out that for addition, it is linear, just like for the first component. So if we take U and then V plus W, right? What we get, we can reverse the order by adding a complex conjugate. So it's V plus W U bar. And this in turn, we can write as VU plus WU bar, right? So this is by property 2. And this is by property 1. Everybody with me? Okay. And now the bar of a sum is the sum of the bars. So this equals VU bar plus WU bar. And then using property 1 again, this equals UV plus UW. Okay, so V plus W is UV plus UW. So the linearity with respect to addition holds for the second component as well. Okay, and it follows from these 3 axioms, so I don't need to write it as an axiom, as another axiom. Clear? Okay. These are fun, right? It's actually a kind of fun playing with these things abstractly. Do you agree? Let's do one more, just for the fun. But it really is just fun. I mean, we need to see examples in order for this to really be something meaningful. Okay, so let's do just one more. What is minus VV, for example? Minus VV. So I can pull out the scalar minus 1 from the inner product. So it's minus 1 VV, right? Do you agree? And I can throw it in. Well, minus 1 is real, so I can put a bar on it for free. It's the same thing. So it's minus 1 bar. Do you agree? Minus 1 bar VV. And once I have an alpha bar out here, I can throw it into the second component without the bar. That's this statement. Alpha bar goes into the second component without a bar, right? So now I can write it V minus V. Good? So this is by this property here. So minus VV is the same as V minus V, and this is true for every V. Good? So these are just a bunch of remarks, and these kind of show you how to prove or find or explore more properties and work with these inner products abstractly. Okay? Let's see examples of inner products on concrete vector spaces that we know. Okay? And what do I mean by see examples? I'm going to give you a formula that somehow takes two vectors and produces a scalar. For example, takes two matrices and produces a scalar. Or takes two polynomials and produces a scalar. Okay? And I'm going to claim, hey, this formula is an inner product. In order to be an inner product, we're going to have to verify that all the axioms in this definition, here's the definition, we're going to need to verify for each of the statements, for each of the examples, that these three properties, look on this board please, that these three axioms of being an inner product indeed hold. Please look on this board. Thank you. So we're going to give examples of concrete V's with concrete formulas that take two vectors, two matrices, two polynomials, two n-tuples, and produce a scalar. And we're going to show that they satisfy these three properties, and therefore they are inner products. Okay? And note that the word product is not necessarily what we know as product, right? So for example, when we had products of numbers, the result was a number. Okay? When we had products of matrices, the result was a matrix. A product of polynomials in the regular sense is a polynomial. Here, this is something really new. Okay? Keep in mind, the product of two vectors is a scalar. Okay? It's really something new. Okay. So, let's do some examples. Some examples. Oh, now I'm already there. Examples. So here's our first example, example number 1. Let's take our vector space to just be the real numbers. That's a vector space. In fact, all the examples that I'm going to give now are going to be real examples. Okay, let's take a peek back at the definition. All our examples are going to be over R, and when we're working over R, things become simpler. Why simpler? Because the complex conjugate business is not there anymore. So we have real symmetry for axiom number 1, and this implies that for the second axiom, when we're talking about the second component, again, we have real linearity in the second component as well, right? Because for the second component, we had here in this remark that a scalar pulls out with a complex conjugate. But if we're working over R, it's just alpha. Do you agree? Okay, so things are simpler when we're working over R, and since we're really not getting into too much details, all the examples that I'm going to give are going to be over R, where things are simpler because this complex conjugate business is not there. Okay? So now let's take the simplest example possible where the space is R itself. Okay? So the vectors are really just real numbers. Okay? And in this case, I can define an inner product by just taking the product. Okay? The product of two numbers is a number. Okay? But we still have to verify that this satisfies all the axioms. So is it true, for example, that I'm not going to write it because it's really trivial, but let's just do it without writing. Is it true that xy and yx are equal? For numbers, yes, it's true because multiplication in R is commutative. Do you agree? Is it true that if we put here a scalar, but a scalar is just another number, right? When V is R, the scalars and the vectors are the same. They're all just numbers. So if you put here alpha x times y, we get alpha xy. Is it the same as putting the alpha out here? Yes, it is. And even writing it is a bit ridiculous. It's just writing it, right? Is it true that if we take x times, or x plus z times y, we get the same as x y plus zy? The answer is yes, and why is the answer yes?
Because it's exactly the same.
No, but why is it true? So why is it true
Because
that x plus z, y equals x, y plus z, y. This is part of property number 2, of axiom number 2 of being an inner product. Okay? So if you're going to say that this is an inner product, you have to argue that this holds. Okay? And the reason it's true is that here what we have is x plus z, y, right? That's how we defined it. And here we have xy plus zy. Do you agree? And why is this true? Why is this true? Why are these two equal? Because R is a field. This is the distributivity property that holds in R. Clear? Good? So sometimes showing that the simplest things hold can be tricky in the sense that you have to understand what you have to claim. Why is it not just, it's trivial? Okay, it's trivial, but there's something hidden here. It's because of the fact that multiplication in R, which is how we define this inner product, is distributive. Good? Okay, and the last property, axiom number 3, was that x times x itself is always greater than or equal to 0, and that's true because xx is just x squared, and x squared is always greater than or equal to 0, and it equals 0 only when x is 0. Okay, good? Okay. Okay, so this is an inner product. This defines an inner product on R. Good? Okay, let's extend that a bit. And let's take V now to be Rn. So now our elements are n tuples. Okay, so for x is now going to be an n tuple, so it's going to be x1, x2, ... xn. And y is going to be again an n tuple, so it's going to be y1, y2, ... yn. For two vectors, I'm going to define x, y. I'm going to define something that I'm going to claim is an inner product. So I'm going to define it as x transpose. That's just making x from a column vector into a row vector. Once it's a row vector, I can multiply it as matrices with y. Okay, a row vector times a column vector gives a number, right? And what is that number? I can even say more explicitly what it is. So it's the number x1, x2, ... xn times y1, y2, ... yn. This is x transpose times y. And what do I get? I get xy, x1, y1 plus x2, y2 plus x3, y3 plus ... xn, yn, right? So I get x1, y1 plus x2, y2 plus ... xn, yn. Do you agree? Or I can write it in summation notation, I equals 1 to n, x, I, y, I. That's the same thing. Do you agree? So the claim is that this is an inner product on Rn. Okay? And this is not just any inner product. So this is called, let's write it here. This is an inner product. Inner product on Rn called the standard inner product. Okay? Clear? So we take two vectors, we just take the sum of the products of their components. Okay? First of all, do you see that when n is 1, so v is just r, then these vectors only have one component, and this sum just becomes x1 times y1, so it reduces to the first example. Do you see that? So the first example is a special case, a particular case of the second example. Okay? Now, why is this an inner product?
It follows the axioms.
Right, we have to verify the axioms. There's no shortcuts, right? So let's think of why the axiom holds. Why the axioms hold. And remember that, okay, let's look again at that board. It's hard to hop between the boards. Let's recall what the axioms are and then verify them, at least the idea. So we're working over R, so we have to have symmetry. UV has to equal to VU. We have to have linearity in the first component. And we need to have that the product of two guys is always non-negative, and 0 if and only if V is 0. Okay, so these are the three properties that we have to verify. Let's just look at this and see if it indeed holds. Okay, so the first thing, is xy the same as yx? Yx is going to be y transpose x. It's going to be writing the components of y here and the components of x here, but the product is going to be the same, right? The product is going to be y1 x1 plus y2 x2 and so on. But these are real numbers, they commute. Do you agree? Okay, so the first axiom holds. What about the second axiom? Suppose we have a little alpha here. Can we pull it out? So if there's a little alpha here, it means it's sitting in each of these components, right? It's alpha x1, alpha x2, alpha xn. It means it's going to appear here as alpha x1, y1 plus alpha x2, y2 plus alpha, etc. Here we can pull it out by distributivity, right? So we're going to get alpha times the entire sum. Alpha times xy. Clear? So that's how you check properties. Okay, I'm not going to do the other two. They're as trivial. Okay, but you need to verify them. You need to spell it out and see that it holds. And usually it's going to follow. Not usually. In these simple examples, it's going to follow from simple properties of the underlying structures, like distributivity. Good? Okay. Let's do a couple more examples, maybe slightly more interesting. Let's look at a space of matrices, for example. So now, in example 3, our V is going to be n by n matrices. And we want to define something, some operation, where we take two matrices, okay, in order for it to be an inner product, before we even think of the axioms, so this is example number 3, V is now matrices, n by n matrices over R. An inner product has to be something that takes two matrices, A and B, and produces a number. Okay, so if we were, for example, to say, okay, let this be A times B. They're square matrices, they're n by n, A times B is defined, but A times B is not a number, it's a matrix. So it's not an inner product because an inner product has to produce a number. Okay? So somehow we need to use some concept that we know from the world of matrices, which takes a matrix or two matrices, and produces a number. How can we, for example, produce a number from a matrix? The determinant. That's a good idea, right? The determinant of a matrix is a number. So it would make sense to write here some determinant that involves AB, maybe the determinant of AB, for example. Okay? You could try. You could try. So it would compile, but you would still need to check the three axioms and see if it is or it isn't. Okay? What I'm going to write is again called the standard inner product on matrices, and it's not going to involve the determinant, it's going to involve the trace. Remember what the trace is? The sum of the diagonal elements. That is again a number. You throw in a matrix, it spits out a number, right? So what I'm going to write is the trace, and now it has to involve AB, right? So it's going to be the trace of A times B transpose. Okay, may look a bit mysterious, but it turns out that this is an inner product, okay, whereas maybe more naive attempts would not produce necessarily an inner product, and it's very good practice to try. Very good exercise. Okay? So let's show that this is an inner product.
That's A times B transpose?
It's A times B transpose. No, if I wanted to transpose everything, I would have to put the parentheses on AB, right? It's the transpose just of B. Okay?
And it's defined as the standard inner product for square matrices? I know, but I was asking if we also use a similar definition for non-square matrices.
No. Well,
because we can multiply them. Well, we could, it's possible.
it's possible what would be your, if they're not square matrices, okay? So you're saying things could extend. I don't want to go beyond the very simple examples that I'm giving here, okay? One needs to check, okay? So you're asking, for example, suppose we take matrices of size m by n, okay? If we take matrices of size m by n, we can't multiply them, but we can multiply A times B transpose, right? Because A is m by n, B is n by m, okay? And then we can take the trace. Is it an inner product? Great question. Verify, okay? So there's a reason that this transpose is here, and okay, good, very good. Let's verify. Here it's going to be less than just more than just an observation to say that this is an inner product. We're going to have to write a bit of stuff. Let's do some of it at least, okay? So this is an inner product. This is an inner product. Let's see what goes into showing that the axioms indeed hold. Okay? So for example, I'm going to verify, let's choose some of them. I'm going to verify some and leave you the others as exercises. Okay? So for example, is the inner product of AB the same as the inner product of B and A? Okay? So what's the inner product of A and B? By definition, it's the trace of A, B transpose. Right? That's how we defined it. Now, recall two properties that we know for matrices. Before we ever discussed inner products, we know that in general, if we take two matrices, A and B, multiply them and transpose, what does that equal?
B transpose, A transpose.
Right. It's the product of the transposed matrices, but in reversed order. Remember this property? So this is a general property. And another statement is that if you take a matrix, transpose it, and then transpose again, what do you get? You just get the matrix back, right? These are very simple facts that we know from our very, very, very first discussion of matrices. Remember, we had a long dictionary of matrix operations, and we proved some of them. I think we may have even proved this formally. Showed that they agree, not necessarily for square matrices even. Okay, for matrices that can be multiplied. We showed that the sizes agree, that the dimensions agree, and we showed that element-wise they agree. Remember how we proved things like this? Okay. Okay, so we know these two properties. So without taking the trace yet, AB transpose is the same as BA transpose. Tell me if you agree. Because BA transpose is the transpose of a product, is the second one transpose, so it's A transpose, which is A, times the first one transpose, B transpose. So do you agree that these are the same? Okay. And now, we know in general that the trace of a square matrix is the same as the trace of the transposed matrix, right? So trace of A is the same as the trace of A transpose, right? Do you agree? So BA transpose, once it's in the trace, I can throw out that outer transpose. It's this. Good? And this, by definition, this equals BA. That's how we, oops. Do you agree? Good? So this proves, by properties of the trace and properties of transpose and properties of matrices, this proves the first axiom. If we define the inner product like this, then taking the inner product of A and B and of B of A is the same. This proves property number 1, which we called symmetry. Good? Okay. Let's look at another property. Let's show, for example, and sometimes what's more complicated to show is sometimes even what looks as a simpler axiom. So why is A, for example, this has to be non-negative, right? Why is it non-negative? Let's prove it. So what is AA? It's by definition, I'm going to erase this or write it smaller. So by definition, it's the trace of A transpose, right? I want to claim that this is non-negative. That's part of axiom number 3, that this is a non-negative number, right? So why is it non-negative? Let's calculate what it is. Okay? So what is the trace of a matrix? It's the sum of its diagonal elements. So it's the sum, I equals 1 to n, of A transpose I. Do you agree? The sum of the diagonal elements of this matrix, which is itself a product of two matrices. Do you agree? Okay, good. This equals, what is the ith element of a product? The ith element of a product. I know the formula in general for the ijth element of a product. If we have in general the ijth element of AB, it's the sum k equals 1 to n of aij, bjk, right? Remember? So let's write that, but now it's II, and now it's special matrices. It's not just AB, it's A transpose. So this is the outer sum, which I'm not touching, I equals 1 to n, and now I'm summing over a new index, k equals 1 to n, and I have to take the ikth element of A, let's call it A I k, times A transpose kj. But I'm not looking for the ijth element, I'm looking for the ith element, so it's ki. Do you agree? Everybody with me? Sure? Okay. What is the kith element of A transpose? Right, it's the ikth element of A. So this is the sum, I equals 1 to n, of the sum, k equals 1 to n, of AIK times AIK. AIK squared. Do you agree? And that's it. This is a non-negative number. These are all, these may be negative. The entries of A may be negative, but their squares are already non-negative, and therefore I'm summing n squared non-negative elements, so this is necessarily greater than or equal to 0. Right? And moreover, it could be 0 if and only if all of these entries are 0. Right? Nothing can cancel out here. So in fact, AA equals 0 if and only if A is the 0 matrix. Do you agree? Okay, so this proves axiom number 3. What remains to prove is axiom number 2, right? The linearity, and I'm leaving it for you to try as an exercise. Okay, you could guess that properties of the transpose are going to show up there, right? We're going to have A plus B or A plus C B, right? And then we're going to throw it into this trace. Things are going to require some properties of either the trace or the transpose. Okay, good? Is the idea clear? Okay, so this thing is an inner product on matrices. You take two matrices, you produce a number that satisfies all these axioms. Good? I want to give you one more example. This last example, I'm going to write it here. This last example is something that you may know a bit, or if you haven't seen integrals in calculus yet, you may have forgotten it since you've seen integrals in high school, but nevertheless I want to write this. So example number 4, I'm going to take V to be the space, the vector space of functions, not even necessarily polynomials, functions defined on some interval AB, okay, functions on some interval AB, and I'm going to assume that these functions are what's called integrable. Okay, and if you don't know what integrable is yet, then you're just going to take it as some property of functions. All it means is that you can integrate them. Okay, you can stick them into the snake. Okay, so if you haven't seen this, a more formal, this word, I'm saying all it is, and like all it means is that you can stick it into the snake. There's like 4 hours of discussion to explain really what it means for a function to be integrable. Okay, so it's I'm really cheating you a bit here. Okay, so, and by the way, this is no longer a finite dimensional vector space. Okay, so this example is really just to show you that things can get very interesting and this thing gives rise to very important stuff. So I'm just touching stuff that's really beyond this course. Okay, so I can define an inner product. Now these are two functions, two integrable functions on AB, and I can integrable, and I'm going to assume they're real valued. Okay, over R. Integrable real valued functions on AB. And I can define an inner product to be the integral from A to B. You don't see many snakes in algebra, right? This is really a calculus-ish sort of thing, but calculus and algebra are not the intersection is far from empty. Okay, so these merge into many topics like functional analysis and and operator algebras and so on and so forth, and I can go on forever here, so I'll stop. Of the product, f of x times g of x dx. This is an inner product. Okay? And if you just think for a minute and you know a bit of stuff about integrals, then you can see that the linearity holds. Okay? So if you take, because an integral is a linear operation, and by the way, notice that we're taking two functions and producing a number, right? The integral from a to b of a function is, at least intuitively, the area under the graph. It's a number. Okay, so we're taking two functions and producing a number. Okay? Okay, so this is an inner product. And there's really no way for us to appreciate the importance of this and things that stem from it at this point. Okay, it's really just, you can call it a teaser. I don't know. It's really hinting to vast, rich mathematics that's beyond our scope right now. Okay? Okay, so this wraps up the list of examples that I wanted to give. I just want to say one more thing, one more definition. Maybe I'll add it here on this board. So what I want to say is that a space that has an inner product is called an inner product space. How's that for a trivial definition? Okay, so let's write it here, up here, definition. If V admits an inner product, V is called no longer just a vector space, but an inner product space. Good? Clear? Okay. So we know what an inner product is. The next step is to see how from this notion of an inner product, which at least thus far still we don't see how from this we get angles. How from an inner product we get angles. How from an inner product we get length. How from an inner product we get distance. Okay, those are the concepts that we wanted to pin down, right? In general, but this does give rise to them. But we're going to see that in a separate lesson, in the next lesson. Okay, so we know what an inner product is. We saw examples. Now we want to see how it gives rise to all these geometric concepts that we had for Euclidean spaces. Okay, that's next. Questions?
Yeah, I have a quick question.
Cool.
If V admits an inner product, it's called an inner product space.
Right.
So that's kind of implying that some V's don't have an inner product.
So again, this is a big topic which we're not getting into. In fact, V can admit more than one inner product. Okay, you can define different inner products on the same space. Okay, so in fact, this is a bit there's a bit of inaccuracy here, because you have to write V, comma, what's your inner product? Okay, and V together with a specific inner product is called an inner product space. Okay, so that's and good question, right? Are there spaces that have no inner products? On the spaces that we've seen, can we define different inner products? Later on, do these different inner products give rise to different geometric structures on the same spaces? Answer yes. Very interesting, very exciting. Beyond our scope, unfortunately. Semester ends in 3 days. Okay? Okay, but I'd be happy to discuss it later if you want. I just we can't afford to go into all this But I hope I'm intriguing you to and tempting you to take further courses along these lines and these ideas. Okay, so that's the end of this one.